if we had a same setup in series, then all the light bulbs would be really, really dim, but in parallel, we would have them light up with equal intensity, but just for like milliseconds.
Yeah,
right?
yeah, before it would kind of die out. Okay, so small class today. Nice Friday, I guess. So last day we covered current resistance, Ohm's law. We talked about resistors in series and in parallel. We introduced Kirchhoff's laws, did a very simple example. We're going to do more today. Today's class I'm going to call the cutoff for next week's test. So whatever we get to the end of today, back to wherever the cutoff was from the last test. I think that was lecture 8. So from lecture 8 to the end of today is the material we'll cover on the next test. I was thinking about the next test. Because we're going to go to a different format, all of our tests so far have been a 12-minute test in a 20-minute period. This test is going to be different. It's going to be a 50-minute test in a 50-minute period. So if you get accommodations, those should already be arranged with the Blumman Center. But because the format is changing a little bit, I'd like to make one new addition to the test. I'm going to let you bring in a sheet of notes if you want one. You don't have to bring a sheet of notes, but if you think that you'll find it helpful in writing the test, you are welcome to make a sheet of notes. There aren't many limitations on your sheet of notes. It does have to be 8.5 by 11. You can't bring in a piece of Bristol board. One-sided only, please, so just one side. If you make it double-sided, I'm going to have to ask you to put it away. I won't let you keep it out. So single-sided, 8.5 by 11, and it has to be your own handwriting. You have to write this sheet. Okay, so those are my limitations on what that sheet is. So before we get started for today, does anybody have any questions? No? Okay, so we're good to get going. So let's do a pretty straightforward example of Kirchhoff's law before we get more complicated. So for people who like a well-defined process, I did write out some general steps in your approach to solving these problems. It becomes more familiar as you do it more and more often, but typically this is everything you're going to do whenever you solve these problems. So our question is going to be, let's find the current flowing through each resistor. So for our steps, the first thing we do is we identify, draw, and label current in every branch. So we have to associate a current with each branch there. So I'm going to say through the middle branch, current is going to flow out of the battery to the right, and I'm going to call that current I1. Current I1 is going to hit this junction. When the current hits this junction, it has two choices. It can go up and left. I'll call that bit of current I2. Or it can go down and right, and I'll call that bit of current I3. Okay, so you should get your currents on your picture. Make sure they're well labeled. You can see what direction they're flowing. Step 2 is an optional step. This is certainly something that I always do. You don't have to do it, and I'll kind of give you a tool to skip this step. And I always label the resistors. When we go with the direction of current flow, it means we go from high potential to low potential. I like putting the areas of high and low potential on the resistors. So our I2 goes from right to left, so positive to negative here. I3 goes from right to left, positive to negative here. That's going to help us when we're writing our potential law to know if we've got a potential increase or a potential decrease. So steps 1 and 2 are done. Step 3, identify loops and junctions. I've already identified my junction. That's my big circle right here. I can draw some loops as well. I'm going to pick 2 loops, and a loop always has to be a closed loop. In this problem, we have 3 choices. We can have our upper loop. So I'll come around like this, and I'll call this loop 1. We can have a lower loop. Come around, and I'll call this one loop 2. And if it were convenient, this outside one could also be a loop. So you could come around the outside altogether. The only thing that matters is that it's a complete closed loop. And I have an example for us to go through where we'll do one like that where we take the outside loop. So I'm trying to get you all the examples. Step 4 is kind of the big step. Write down the laws, the current rule and the loop rules, and solve the problem. So let's start by writing down our current law. Current law says that the net current into a junction equals the net current out of a junction. The current in is I1. The current out is I2 plus I3. Okay, so there's our current law. We drew 2 loops, so let's write 2 loop rules. So we'll go with a rule for our loop 1. So our generic loop rule is that the net potential, so delta V of the battery, plus the potential across the 18 ohm resistor, delta V 18, plus the potential across the 45 ohm resistor equals 0. I would say in practice when we solve these problems, we don't really write down this step. We kind of do this step in our head, but I will write it down for this example. So as we go through here, we have to remember about potential increases and potential decreases, and we have to make sure we get the signs right. Is it an increase or is it a decrease? So as we come around loop 1 comes from this side to this side. We go from a negative potential to a positive. That's a potential increase. So associated with our battery is a potential increase of 25 volts. Typically when I solve problems in class, I'm kind of a stickler for including my units in every step as I go along, and I think that's a good habit because it helps you keep track of your units. I'm not going to do that in these equations just because it really gets a bit visually tangly and it's hard to see everything for all the symbols. So 25, that is in volts, but I'm not going to write my V for volts this time. Okay, my potential across the battery. So we see we go from a high potential to a low potential. That's a potential drop. Potential difference, delta V is I times R. So I've got my resistance, 18 ohms, times the current flowing through it, which is current I1. And then I come to my next battery. As I come around my loop, I see that my loop goes from a plus to a minus, high to low, so it's a potential drop across the 45 ohm resistor. 45 times I2 equals 0. Okay, any questions here? Okay, so here's where I'll talk about the plus minus business and the rise versus the drop. So when you're doing these, if you don't like labeling your resistors as positive minus to see if you're going from a high to a low, what you can see is that if your loop matches your current direction, if they're in the same direction, then you will always get an increase with a battery and a decrease with the resistor. If your loop and your current direction are opposite, you get the opposite behavior. You get the drop over the battery and the increase over the resistor. So if you like to think about it that way, no problem, whatever suits you better. So right now, I've got a problem where I still don't know anything. I've got I1, 2, and 3 here, I1 and I2 here. I don't know anything, I'm stuck, so let's write our loop 2 equation, and then we're going to start to solve it all together. So my loop 2 equation will start delta V of the battery plus delta V of the 18 ohm resistor plus delta V of the 15 ohm resistor to give us 0. Delta V of the battery, we go from minus to plus, or the loop agrees with the current, so we get an increase of 25 volts. My potential across the 18 ohm resistor, the loop and the current are the same direction, or we go from high to low, so that's a potential drop, minus 18 ohms times current I1. For my 15 ohm resistor, my loop and my current I3 match, or I go high to low, that's a potential drop, minus 15 I3 equals 0. Now what I have is 3 equations, 3 unknowns. This is something I can solve. So I see that from this equation, I can write I can write I2 in terms of I1. In this equation, I can write I3 in terms of I1. So I'm going to do that for these equations, and I'm going to plug both of those things in here. I'm going to solve for my I1, then I'm going to come back and find the other currents. So there's my algebraic strategy. So for this equation, 15I3 equals 25 minus 18I1. I3 equals 25 over 15 minus 18 over 15 times I1. At this point, if you're a fractions person, you're probably going to leave it in fractions. If you're more of a calculator person, you might put this in terms of numbers. 1.667 minus 1.200 I1. If you're going to go to the decimal format over the fractions, I would suggest you keep a few extra sig figs, just so you don't get too much rounding error in these problems. It can be a little sensitive to rounding. Okay, from loop 1, let's solve this so it says I2 equals something in terms of I1. 45 I2 equals 25 minus 18 I1. I2 is 25 over 45 minus 18 over 45 I1. I2 is equal to 0.5556. Take away 0.4 I1. So now I'm going to pop this in for I3 in my current law, pop this in for I2 in my current law, then I can find my I1. Once I have those, I can find my other currents. So I1 equals I2, which is 0.5556 minus 0.4000 I1. I've got to break down onto the next line here. I don't have quite enough room. Plus 1.667 minus 1.2 I1. Get all my I1s on one side. And my numbers on the other side. So 1 plus 0.4 plus 1.2 I1 equals 0.5556 plus 1.6667. I1 equals 0.855 amps. So my current I1, the current going through the 18 ohm resistor, 0.856 amps. 855, sorry. Any questions about this bit? The algebra is kind of boring. I won't do it too often in class. All right, then we can come back to loop 1 and find our I2. I2 is equal to 0.214 amps. So that's the current through the 45 ohm resistor. And then we can come to our equation for loop 2 and find that current I3 is equal to 0.641 amps. Okay, any questions of any of this stuff? When I drew my currents, and this part is kind of important, when I drew my currents, I would have to say that I didn't definitively know the direction of the currents. I guessed. It was an educated guess. I thought I was right. I was pretty sure I was right. But it was just a guess until I finished the problem. If I had guessed incorrectly, do you know what the difference in the answer would have been?
Negative side?
I would have had a negative current. So if you work through the problem, and when you're newer to the problems, you may not have that instinct for getting the right direction of current. If you ever get a negative direction for your current, it just means you picked the wrong direction. Okay, so if I had chosen I3 to come up this way, I would have gotten a negative value for I3. Okay, any questions? Let's do another example. So let's go to a problem where we have two sources of potential. Kirchhoff's laws are a really nice way of solving problems with multiple sources of potential. We'll do all of the same steps. So to start this problem, we've got two batteries, two resistors. We'd like to find the current through each resistor, so there are two currents here, and the potential across each resistor. We could probably do a shortcut here, and the shortcut would be the 30 ohm resistor is in parallel with the 10 volt battery. If they're in parallel, they have the same potential. You could use V equals IR to find the current. I don't want to go through the shortcut because I want to model the process of solving Kirchhoff's laws. So we'll start by labeling our currents in our circuit. So I'm going to say current comes out of the positive terminal of the 10 volt battery. I'm going to call that current I1. Current comes out of the positive terminal of the 5 volt battery. I'll call that current I2. So the current I2 is coming around this branch this way. And then I have current I3 running through the 30 ohm branch. It's hard to tell which way it goes. I'm going to pick that it goes down. Okay. So I've labeled my currents. I'd like to identify my junction as I get started. I'll identify this as my junction because I can see that current I1 goes in, I2 and I3 come out. So I've drawn and labeled my currents. I've written down my junction rule. Next, I'd like to identify my loops and write down my loop rule. So I'll pick the loop on the left to be loop 1. I'll come around my loop this way. For this loop rule, I've got a potential increase of my battery, 10 volts. I've got a drop across my resistor, so my current flows from positive to negative, or you can see that your loop matches your direction of current of I3. So I've got minus 30 ohms times I3 equals 0. This statement right here, this loop 1 statement, is the same thing I said about the 30 ohm resistor being connected in parallel with the 30 volt battery. I see that they have the same potential. So right off the bat, I can take this equation and solve for I3. I3 is going to be 10 volts divided by 30 ohms equals 0.333 amps. So I've got my I3 done. Now let's go to my second loop. Take my second loop to be the one on the right. I've got to pick a direction for that loop, so I'll pick this direction right here. This will be loop 2. I'll write my loop 2 rule. So I can label the ends of my resistors. So for my loop 2 rule, let's start with the battery. I go from the negative end to the positive end of the battery. That's a potential increase, plus 5 volts. Or loop 2 matches current I2, so I've got to have a potential increase with my battery. I get to my resistor R3. Here's the case where it's opposite. As I come around loop 2, I go from the negative end of the resistor to the positive. I go from low potential to high potential. This is where I get a potential increase across this resistor. Plus 30 I3. If you prefer the other way, I see that my loop comes up, my current comes down. That gives us the opposite behavior, so instead of having a potential drop, we get a potential rise. So 2 ways to think about it. I get to my 20 ohm resistor, my loop matches my current I2, so I've got a drop across this resistor equals I times R, 20 ohms times current I2. So there's my loop rule for the loop on the right. In this equation, I've now figured out I3, which means I can go ahead and calculate I2. So 20 I2 equals 5 volts plus 30 I3. I2 is 5 volts plus 30 times I3 divided by 20 ohms. Gives us current I2 0.750 amps. So there are my currents I2 and I3. Now I can come back and find my current I1. I1 is I2 plus I3. So 0.75 plus 0.333, 1.08 amps. So now I've found the current in every branch. Now I can just do my answer nicely. I'm asked for the current through each resistor and the potential across each resistor. So let's look at each resistor and make sure we can figure out our answer. Let's start with the 30 ohm resistor. So my 30 ohm resistor has current I3 running through it, 0.333 amps. That current flows down. So there's my current. The potential is current times resistance, I3 times 30 ohms, equals 10 volts. If you were doing this problem on a test, and if you didn't find your potential this way by doing IR, if you instead said that you could see that this resistor was in parallel with this battery, therefore they had the same potential, that answer is also correct. Okay, so two ways to give the same answer there. You can do IR, or you can recognize that they're connected in parallel. For our 20 ohm resistor, current I2 flows through it. I2 equals 0.750 amps. That also flows downward. And the potential across this resistor is I2 times 20 ohms, or 15 volts. Okay, any questions there?
Yeah, so I'm a bit confused about I2.
Yep.
Is it due to the 5-volt battery, or is it due to the splitting of I1?
Oh, that's a good question. And the answer is it's because of everything, right? When we put these two batteries together, this is just the way the current is going to flow in this circuit. So current flows out of both these batteries. Current splits here, and current flows out of here. What we see here is a combination of both of those things together. Yeah.
Could it be that I2 splits into like two currents at that junction?
So for example, we could come here. Here is I2, I3 goes up, and I1 comes out this way. Yep, that would be a valid way to treat it as well. Yeah, you would get the same results.
Thank you.
Might be a good homework problem to try. Because you already know the answers, right? You know what to expect. Okay, so the next one in the notes is the same kind of a problem. It's just got an extra resistor in it. I'm going to call this one a homework problem. I'll post the answers. I've got it laid out nice and clearly, but if you have any issues with it, let me know. And then we can either do it in class or we can talk one-on-one, depending on how many people get confused with it. We are going to keep doing these problems, but we're going to do them in context of looking at voltmeters and ammeters. We're not leaving Kirchhoff's laws behind. We're just going to layer in an application with it. So we're going to talk about ammeters and voltmeters next. Ammeter is a device that measures current. A voltmeter is a device that measures voltage or potential. I know you use them in labs all the time, but now we're going to talk about how they work and kind of what's the properties of those devices. So we'll start with the ammeters. So to start with, let's just assume we have a simple circuit where we have a potential source epsilon, and it's connected to a resistor. I labeled it 6 ohms, so we could do numbers if we wanted to. We could also just call it R for resistance. If I have this circuit, we know current is going to flow through the circuit, so the current will come out of the positive end of the battery, come through. That current we can label I. And in this, if we wrote a loop rule for this circuit, we would have that epsilon minus IR equals 0. I would be epsilon the potential divided by the resistance. Okay, so that's kind of the most basic circuit we could do. So we know what current we should have. What if we wanted to set up this current and we wanted to measure it? Well, that's when we would use a device called an ammeter. We would disconnect the wire here from this resistor. We would plug in the ammeter so that it connected to the resistor. If we want to measure current, then we have to connect the ammeter in series, right? It definitely has to be in series. So here's a picture of our ammeter in series. So then, if I'm insisting it has to be in series, you might ask, why does it have to be in series? So why would an ammeter have to be in series?
Because when current is flowing in series, that's when it's equal.
Exactly. Anything in series has the same current. So if we want an ammeter to read current, it has to be in series with the thing we want the current of. So things in series have the same current. So that's our third point right here. So let's ask, so we're going to plug our ammeter into the circuit. An ammeter is a device. It's a physical device. You can go buy one at Princess Auto. If it's real, then it has a resistance associated with it. It's not ideal. It's a real thing. So it's a good idea to ask, what's the impact of putting our ammeter in series? So this ammeter is going to have a resistance. That we might call R with an A on it. So let's think about, what does the addition of this resistor do to this current? Because ideally, we don't want it to have much of an impact at all. You don't want your measuring devices to change what it is you're measuring, otherwise it's pointless. So let's see the impact and see what that tells us about this resistor. Let's do a loop rule for this circuit. So we'll draw our loop coming around this way. We've got a current coming out of our battery. I've just said that if we put the ammeter in, it might change the current a little bit. So maybe I'll label this current I prime, right? So maybe it's a little bit different. Let's just see what the deal is. I'll write my loop rule. So my potential is epsilon. I get a drop across the ammeter. And I get a drop across my resistor. I solved this expression over here for the current. Let's solve this expression for the current. So my current is going to be the potential divided by the total resistance. I want those two currents to be the same. I don't want my current to change. So if I don't want the current to change, my original current is epsilon over R. My new current is epsilon over R plus the resistor of the ammeter. If I want these two to be the same, I want this number to be really small, right? I don't want to change my denominator very much. So when you build an ammeter, you have to build it so that it has a very small resistance. Okay. So we want a small resistance of our ammeter so that when we insert it, it's not going to change the current in the circuit very much at all. Okay, questions? Okay, let's do an example that has an ammeter in it. So in this circuit, I've placed two ammeters. This ammeter reads a current of 150 milliamps. This one reads a current of 388 milliamps, and I'd like to figure out the potential of the battery. And then for homework, we'll find the currents through these two resistors right here. So when we do these problems, one of our first steps is to draw the currents through the circuit, identify any junctions, draw the loops, write our loop rule, and then solve the problem. So that's the general strategy. Let's label the currents first. So I'm going to say the current comes out of the positive end of the battery. Here's my current, I'll call I1. That's the current that flows through ammeter A1. So I know I1. The current comes to this junction. So some of it is going to go forward. That current I will call I2. Some of it is going to split down through this branch. I'll call that I. And then it splits into I3 and I4 down through these branches. Okay, so I've labeled all my currents. I've shown a couple of junctions. I can write a current log. I think I'm not going to do that just yet. I know my current I1 that runs through the 15 and the 12.5. I know my current I2 that runs through the 8.45 and the 4.11. I can pick my loop very judiciously so that it's straightforward to find my epsilon. So for my loop choices, I can draw a loop right here for this circuit, the one on the left. I can draw a loop in the middle, and I can draw a loop on the right, or I can draw a loop through the whole outside thing. Right? So I've got 4 options of where I can put my loops. I think, because I know these currents, and I want this potential, I think this outside loop is going to be the one that gets me where I want to go. So I'm going to label that loop. So there's my loop, and we'll write our loop rule. So for my loop rule, I've got a potential increase due to my battery. I've got a decrease over my 15 ohm resistor. I've got a decrease over my 12.5 ohm resistor. I've got a decrease over my 8.45 ohm resistor. And a decrease over my 4.11 ohm resistor. And they all have to add up to be 0. So the potential of my battery minus 27.5 I1 minus 12.56 I2 equals 0. My potential then is 27.5 times my current I1, 0.150 amps, plus 12.56 times my current I2, gives me a potential of 9 volts. If you had picked this loop right here, that would have introduced current I3, and this loop over here would have introduced current I4, you could certainly solve those problems. You can do your loop rules and find currents I3 and I4. It would just be more steps. Okay? And then to do the homework problems, you will draw those loops. So you will draw a loop right here. That'll let you find current I4. And then draw a loop right here to let you find current I3. So you can do those loop rules and find those currents, but if you had started there, you just would have done more algebra. You would have done the homework first and then got to the first question at the end. Does anybody want to see those loops and rules, or are we good? I am going to post the answers, of course. Why don't I just write down what the 2 loop rules are, and then we can leave it. So if we did a loop over here, so we would have a drop across the 8.45. We would have a drop across the 4.11. And then we would get an increase across the 17.2. Use that to find I4. And then you've got 2 choices to find I3. You can use a loop out here, or a loop in the middle. I think the loop in the middle might be the easier way to go. So if we pick a loop in the middle, come around this way. So we've got to drop across the 17.2. And get an increase across the 13.8. And you can find your way through. So for your Kirchhoff's laws, you're basically just picking loops and writing down equations. Okay, and then I'll just sort of calculate those numbers and post it with the homework if you want to check it. Any questions? So let's move on to voltmeters. So for our voltmeters, we use those to measure potential. So let's say we start with our simple circuit. We've got current I flowing around it. We've got a battery connected to an ammeter so we can measure that current. We know that ammeter has a small resistance. We've also got a resistor here that has a resistance that we'll call R. If we write a loop rule, epsilon minus I times R equals 0. When we do these problems, sort of after we do the setup to show how these things work, in the future when we do these problems, we do assume our meters are ideal, that we don't get any drop across the ammeter. Okay, so at this point we're assuming that this ammeter is ideal. So if we want to measure the potential, we want to measure it across something. Let's say we want to measure it across the 6 ohm resistor. If we want to measure potential of something, we need to connect it in parallel because things in parallel have the same potential. So we take a voltmeter, we take the 2 leads out of the voltmeter, and we stick them on top of the 2 leads going to the 6 ohm resistor. So now the voltmeter is connected in parallel, so it has the same potential. So we'll ask, what's the effect of inserting the voltmeter? Because it's a real device, it does have resistance, it can draw some current, so let's see what happens when we hook that up. So let's have our battery draw the same current I that's being read off that ammeter. That current comes to a junction and it splits. Some of the current goes down through the branch with the voltmeter in it. I'm going to call that current I with a V on it for I through the voltmeter. Some of the current goes down through the branch with the resistor in it. That's I of the resistor. Okay, so the current that comes out of the battery splits because it hits a junction. It has 2 places to go. Let's write our current law. Our current law says that the net current emitted by the battery going into that junction is equal to the current out of the junction, which is the current that goes through the resistor and the current that goes through the voltmeter. What we want to have is for when we connect this voltmeter, for it not to appreciably change the circuit, we want this IR to be about the same as this current. So we want those to be the same so that this voltmeter is not drawing too much of the current. We don't want the current to change. Well, if the current through the resistor is about the same as the current through the battery, it means we do not want the voltmeter to draw very much current at all. We want that current to be about 0 so that most all of the current is driven through the resistor because that's what it looks like in this circuit. We want it to stay the same. So if that's our case for our currents, let's ask what happens when we apply our loop rule. So let's draw a loop right here. So we get a potential drop across the voltmeter minus current times the resistance. Say that the voltmeter has resistance of an R with a V on it. So minus I through the voltmeter times resistance of the voltmeter, we get a potential drop across, increase across the resistor. Equals 0. So We figured out that the resistance of the ammeter had to be small. Let's ask what's the resistance of our voltmeter. So the resistance of our voltmeter is going to be the resistance through the resistor times the resistance divided by the current through the voltmeter. Well, we already said that this one had to be really small. Therefore, the resistance of the voltmeter equals very big. So when we put something with a big resistance in parallel with another object, less current will flow through it because it's harder to flow through it. Current will always flow through the branch with the lower resistances. So our voltmeters have to have big resistances, so it draws a very small current, and mostly all of the current is pushed through the resistor so that we get this unchanged circuit. So that's how a voltmeter works. Okay, questions? Okay, let's do an example of the voltmeters. So in this circuit, the batteries have negligible internal resistance. The meters are both idealized. So that means we're saying that the resistance of the ammeter is 0, it doesn't change the circuit. The resistance of the voltmeter is basically infinity, it doesn't draw any current. With the switch open, so this switch broken, the voltmeter reads 13 volts. Find the EMF of the battery. And what do we get on the ammeter when the switch is closed? Okay, so let's talk about what happens with the switch open and the switch closed. So to make it easier for me to draw the diagram so it wouldn't look so terrible in your notes, I just reprinted that diagram by itself on its own slide. So hopefully it just won't be too blurry. So let's think about all the currents. Let's draw and label those first. So I'm going to have current coming out of my battery. I'm going to call that current I1. The current comes up here to this junction. The current is going to split. So some of it is going to come down through right here. I'm going to call this current I2. And some of the current is going to go forwards. I'm going to call that current I3. Part A of the problem is what we're doing right here. And that says with the switch open. So if the switch is open, does any current flow in this branch right here with the switch open? It's a broken circuit, right? The current can't go anywhere. So that battery has no effect if that switch is open. So it's like that branch is not even there because current can't flow through it. It has no impact on the circuit at all. So this is what happens when the switch is open. So then for our current I3, let's see what happens to that one. It goes through the 30 ohm resistor, goes on through the ammeter, down through right here. This is an idealized voltmeter, so the current that comes through I3 comes through the ammeter, comes down to this branch. None of it goes through the voltmeter. All of it goes through the 50 ohm resistor, comes back around this way. Okay, so that's what's happening to those currents. So you got to be careful with your ammeters and voltmeters, kind of know where the current goes. Any questions about those currents? Those all good? All right. So they look fine. So now let's think about our loop rules. What could we figure out here? So if I want to pick my loop rule, and I'm trying to find the EMF of the battery, if I want to find the EMF of the battery, it means I'd like to have current I1. I don't know current I1, but I can probably figure out current I3 because that voltmeter is connected to it and I know the potential across it, so I can find current I3. If I find I3, then I can find I2, and if I find I2, then I can find I1. Okay, so let's kind of start putting some of that stuff together. So let's look at what's happening right here to the 50 ohm resistor. The voltmeter reads 13 volts. So that means there's 13 volts across my 50 ohm resistor. If we apply Ohm's law, V equals IR, then the current through the 50 ohm resistor, which is what we called I3, is the potential divided by the resistance, 13 volts divided by 50 ohms. 13 over 50, 0.26 amps. Okay, so now I have my I3, and I could find my I3 because I knew the potential across the resistor. Now that I have my I3, I can do a loop rule to find my I2. So I'll draw my loop. So there's my loop, and I'll write down my loop rule. So for my loop rule, so I'll start right here. I get a potential drop across the 30 ohm resistor, minus 30 times I3. Then I get to the 50 ohm resistor, I get a drop there, minus 50 I3. Keep coming around, I get to my 75 ohm resistor, my loop goes up, my current comes down, I get a potential increase, so I've got plus 75 times I2 equals 0. Okay, so from this outer loop, I can find the current I2. So I2 is 30 I3 plus 50 I3 divided by 75. I3 is 0.26 amps. 0.277 amps. Okay, so I've got I2 and I've got I3. That means I can find my I1. So I go to my junction law. I1 equals I2 plus I3. 0.537 amps. And now, one more loop rule, and I can find the potential of my battery. So there are two loops I could take. Both would give me the same answer. I could take the loop out here on this side, or the little loop on this side. I think I'll take the little one on the inside. So I'll draw this loop right here. My loop rule says my potential of my battery, minus 20 I1. Minus 75 I2 equals 0. I know I1, I know I2. I can find the potential of the battery. .5 volts. Okay, any questions? Okay, the part B should be really fast as well, should be faster than that bit. So part B asks, what will the ammeter read when the switch is closed? So for part B, we're going to close the switch. If we close the switch, current is allowed to flow. Okay, so now my switch is closed. For this one, I'm trying to get the reading I3 here. Let's look at what's happening in this branch. So all I have in this branch is a 50 ohm resistor in parallel with a 25 volt battery. Because they're in parallel, that means the potential across the 50 ohm resistor has to be 25 volts. The current that flows through the 50 ohm resistor is the same as the current that flows through the ammeter. So I is V over R. 25 volts over 50 ohms, 0.5 amps. You would have got the same thing if you did a loop rule, so 25 volts minus 50 times I equals 0. I equals 0.50. Two different ways to think about it that give kind of the same answer. Okay, that takes us right up to 1250. So when we're back on Monday, we'll be able to start RC circuits.